Hello all and welcome back to this course on computer organization. So having studied the construction of a simple RISC V processor for a small subset of instructions, but a very representative set of instructions which basically capture the essence of all kinds of instructions that are needed in the RISC V processor. Let us now move on to analyzing the performance of a single cycle processor like RISC V that we just implemented. So how do we quantify the performance, right? When we want to say, okay, there is an x86 processor, there is a RISC V processor. The x86 is a complex instruction set computer which allows all sorts of instructions. Visibly, the code that that a C compiler spits out is much smaller with much fewer instructions compared to what a RISC V compiler puts out. Now, how do we compare these two architectures, right? Ultimately, what really matters is this is a computer, this is going to get used by somebody, this is going to get used by some application, and therefore all that really matters is the program execution time. Okay, now what kind of programs? So what kind of programs? Basically, we have a certain very specific set of programs for each kind of computer. For example, a desktop computer, or something which is going to be used to play games will be benchmarked with a certain program that involves gaming. If you have a server, then you're going to involve some database operations. A lot of things are going to happen, so there will be certain other kinds of programs for that, and these are called benchmark programs, right? So all you need to do is to actually take these benchmark programs, compile it on each of these processors, and then look at the execution time of that particular program. Okay, now what is the program execution time given by? It is basically the number of instructions. So if you have more instructions in the program, it is true that you are going to take longer to execute, right? Into the cycles per instruction. What is cycles per instruction? It's basically the number of clock cycles that are needed for you to complete the execution of that particular instruction. Now it turns out in the single cycle performance that we are going to quantify now, by definition every single instruction is going to take exactly one clock cycle, and therefore cycles per instruction, CPI, is going to be 1 in this discussion that we are going to have. And then I need to multiply it, right, by the clock period, because I have now said number of instructions, each instruction takes one clock cycle, therefore it's simply the number of clock periods that are needed into the clock period that basically is going to give you the program execution time, and therefore it's number of instructions into CPI into the clock period, right? So this is what we are going to do. Now the key point to note here is that the number of instructions might be much larger for RISC V compared to an x86. However, and if you compare a single cycle execution of x86 and a single cycle execution of RISC V, the CPI is the same. Both will take only one clock period, right? One clock period per instruction. However, it is the difference in the clock period that is going to determine which architecture is faster and which architecture is better. As you will see by the end of this discussion, it turns out that the more complex instructions you add into a microprocessor, it is simply going to increase this clock period time for you, and therefore it is not beneficial to add very complex instructions into the architecture. So before we jump into the whole clock period analysis, it is important for us to understand what are the timing elements that we are talking about. So remember that we went ahead and built our entire computer using just some very elementary blocks like this. Basically the program counter, which is a register, okay, PC next is the input, the PC comes out at the clock edge, positive clock edge, and then the whole operation starts, right? You fetch that instruction from memory, then you decode, you execute, and so on, right? So there is a program counter, and associated with this is basically a TP PCQ of the PC. Okay, that's what you see here. What is TPCQ? It is the propagation delay, clock to Q delay. So after the clock edge, how long? So if you look at this, we are talking about the clock edge going up like this. Okay, clock, then my PC next is ready here. Okay, and of course that has to be ready some setup time before. Okay, so this is some state 0, it goes into the first instruction, right, address, then my PC is going to come out of this, right. So from this clock, remember we are talking about the TPCQ of the program counter, right. So let me put that in red here, TPCQ of PC, right. Then there is a register setup that basically is needed for you to set up the data, right, and we are talking about this setup time. So you want, you know, all your data to be ready before the next clock edge, right. So that is what we are going to call T setup. So you will have a T setup here, right. After that, what is not shown here is also we did have a couple of multiplexers, right, simple 2:1 multiplexers like this, right, or maybe 3:1, 4:1, right. So what is a multiplexer? Basically a multiplexer is nothing but a decoder followed by a tri-state inverter, right. So there is a mux delay that we are going to talk about, right. This could be, it's not a very large mux, so it's just about 2 input. Of course each input could be 32 bits, so it could be 32 muxes, 2:1 muxes in parallel, right, but or 4:1 muxes, right. So we are talking about some small mux like that, and we are talking about T mux is basically this delay, T mux, right, the delay for the input to go to the output, and that's what we are talking about here, right. Then there are some very simple logic gates and or delays, and that we are going to say is about, that's what we are going to call as T and or. So I will annotate this at a later point. After this we had the ALU. Okay, again the ALU was just denoted as one large block like this. Okay, basically it had 2 operands, right. Some ALU1, ALU2, and each of this is a 32-bit number, right, 32-bit bus, and you get an output of this. Now what operation you are going to do is going to be selected by some other ALU operation, if you remember, right, and this time, the ALU time is going to be characterized by the longest operation that that it can do, right. So it could be, for example, addition. If the ALU does multiplication, then multiplication is probably the operation that takes most time, and therefore this is what we are going to call as TALU. Okay, the slowest operation of the ALU. Now you also have the decoder. So in the control unit there was a decoder, and that needed some time to decode, right. So that is what we are calling as the T decode here. So I am not going to draw that here, that's just a simple decoder there. Then we had this extend unit. Extend unit was, because we had only 12 bits of immediate data, we needed to extend it to 32 bits, which was just sign extension. But more importantly, the immediate data format was different for different types of instructions, and therefore that needed some decoding, right. So therefore the extend unit is what we are calling as this T extend, right. So if you remember, we represented the extend unit like this, Okay, we are drawing it this way because data is coming in as some 12-bit, 20-bit, some very small bit format, but it is going out as 32-bit. And there is something here which is going to help you decode this, and right. So this delay is what we are calling as EXT, right. Then you have the memory read. Now we had two kinds of memory. One was the instruction memory and the data memory, okay. And therefore, after the address has been presented, it is going to take a time of T memory, T mem, to actually come out onto the data bus, on the RD bus, right. So this is what we are going to call as T mem. Likewise here also, when we read, we are going to associate a T mem with this particular memory. So note that the numerical value of this T memory seems to be the largest amongst all the delays that we have considered, right. So the delays shown here are very representative for a given technology. Even if you go to a newer technology, the delays may scale, all of them will scale down, right, but the relative magnitude will still remain similar, you know, in order of magnitude, right. Memory read will be the highest and so on, right. So finally, what we do have is, when we operate on the register file, you could do two things. One is you will want to read data, okay, out of the register file, and therefore that we are calling as TRF, register file read. Now what is this time? We are talking about presenting an address and then getting the data out. Now the register file, if you remember the implementation, we just had 32 register files and one big mux, 32:1 mux, that got data out onto the one read port. If you wanted two read ports, you had two muxes, right. So you present an address and this 32:1 mux has to sort of, you know, decode this address, then select it, generate the select signal, then the tri-state inverter has to select them. All of them will happen 32 bits in parallel. So effectively it is going to be this decoder plus tri-state inverter, again just like that other multiplexer, just that this is a much larger multiplexer that we have, and therefore this delay, if you look at it, it is much larger than the T mux that we spoke about. Why? Because it's simply because it's a much larger mux. It's a 32:1 mux. So the decoder is larger, it takes longer, everything, right. Finally, when we do some R type of instruction, right, when there is a destination register that is involved, it could happen even in I type of instruction. When there is a destination register involved, you have to come back and write data into the register file, and therefore you have to set up the data before the clock edge. How much before? Setup time before, and that is what we are calling as this TRF setup. Okay, so that's the other timing that is associated with this particular block, right, for the register file. So this TRF setup, remember, is again, if you look at it, it says about 60 picoseconds here. Register setup is about 50 picoseconds. So these two numbers can be slightly different, okay, because of the there is a write enable involved in this register file, right, whereas the PC, there is no write enable involved, okay, and write enable means there is a mux sitting before the flop, okay, and that delay about 10 picoseconds is going to increase the setup time of your T register file setup. So that will be slightly larger than your register setup without a write enable, essentially, right. That's the difference. So these are the delay elements that we are talking about. Their values are given here. Based on this, we are going to go ahead and analyze the different kind of instructions, the time it's going to take for different kinds of instructions. Okay, so what are the kind of instructions that we spoke about? Okay, so the instruction that we are talking about, okay, is one. It could be add x1, x2, x3. Okay, what type of instruction is this? This is the R type of instruction, right? Then I could do add I, right? Or maybe I'll write everything in lowercase because that's how it is. Add I, x1, right, x1, x2, immediate data, okay, and this is I type of instruction, okay. Then you have, you could do a load word, okay, a load word which is basically some x1, x2 minus 10 of x2, right, load word. This also happens to be an I type, okay. Then you can do a store word, right, x1 minus 10 x2 again here, right. Then you could do a branch on equal, right, which basically is x1, x2 and immediate data, right. If I am not mistaken, that is the format that we used for the branch on equal type of instruction. So let's just be sure about that. I type branch on equal, yeah, so we are doing this. So yeah, BEQ, X4, X1, X2 and L7, right. So that was some sort of data. So what is this? This is the store, this is the branch type, right. So maybe what I'll do right now is I will not worry about this immediate data, right. I will not worry about this immediate data, okay. I'm going to only worry about one instruction of each type, right, because the load word also happens to be a I type instruction. Now, how do we go ahead analyzing this particular timing, right? How do we find out what is the maximum clock frequency that will accommodate this particular instruction? That is the question that we are trying to ask, right? So, ideally, I would like to build a computer and just run it at like, 100 gigahertz, right? But what stops me from running it at 100 gigahertz, right? So, there is a static timing analysis that needs to be done, okay, in order to figure out the maximum clock frequency that is permissible for each type of instruction. We'll do it for different kinds of instructions and then come to a conclusion of, for this computer, what is the clock frequency that is going to work, right? So let's start with the R type of instruction. Now in any static timing analysis that involved a clock frequency, if you remember, we always drew it like this. There's a combinational block and it is sandwiched between two flip-flops, right? So this is a clock, right? So in some sense, this was the launch flip-flop and this was the capture flip-flop that was basically going to capture the data, right? So the launch flip-flop basically launches the data, okay, and the capture flip-flop has to capture this data appropriately, right? So if you look at the clock here, you have some data coming in ready for the flip-flop FF1 to launch, right? So on the positive edge of the clock, that data goes through. Then it's a combinational block. See, that means once the input is presented to the combinational block, after a finite propagation delay, right, you are going to get that output changing at the at the output of the combinational block, and that needs to be captured at the next rising edge appropriately. So therefore, there was a, we said that the clock period should be greater than TPCQ of flip-flop 1, right, of the launch flip-flop, plus the propagation delay of the combinational block C, right, plus T setup. right? This is what we needed in order to ensure that the data is captured appropriately. So as long as the clock period is greater than this, right, it will work, and therefore the maximum clock period that will work is basically F max is 1 by TC max. And what is TC max? TC max is basically this value. It is just exactly this value, right? I'll say 1 by TC min, I'm sorry. Yeah, because it is greater than, supposed to be greater than this, right? So therefore, in order to do this static timing analysis, the first thing you need to do for every kind of instruction is to identify which is your launch flop and which is your capture flop, okay? So let us go ahead and do that. Launch, okay, launch and capture. So okay, I'm going to put this here. Okay, this is the diagram that we sort of constructed earlier for the single cycle processor, and we are going to use this for analysis. This blue line here doesn't mean anything. Okay, this result source, it's just the last diagram that I have taken out of there. Now what we find is that the first step, okay, of a microprocessor execution is to update your program counter with the next instruction, right? So you might want to start first. Let's say at boot up time you're saying start here. So this PC next will have to have some path to say, okay, load some initial value, okay, and then you pulse the clock. The moment you pulse the clock, remember there's no write enable or anything here in this register, it will just get written by default, okay, and that data is going to appear at the thing. So for any kind of instruction, it is your program counter that is your launch flop, okay. Even for I-type store or branch, whatever it is basically the PC. Now what is going to happen for the R type of instruction? Okay, so let us look at this. Very specifically, we have taken an example, add x1, x2, x3, right? So x2 and x3 will be added and the result will be put into x1. So what is going to happen? Eventually you are going to, fetch data, okay, from the register file x2 and x3. You're going to read it, you're going to send it to the ALU, and then you will write it back into x1. Therefore, the capture flop in this case happens to be the register file. In specific, we are talking about the register x1 in this example that we chose, okay. Now what does load word do? Okay, load word is basically some sort of I-type instruction. You're doing x2 minus 10, taking that from memory and you're putting that into x1. Okay, this is what you have, and if you want to do this, then effectively what you need to do is get the register data out of x2 first, then subtract this immediate data, treat that as an address, fetch it from the data memory, then you come back and write. So again, the capture flop in this case is just x, the register file again, x1, okay. Now store word is a slightly different operation. So basically what you're trying to do is, again you're trying to calculate an address, x2 minus 10 here, right. So this is x2 minus 10, right. This address you are trying to, into that address you are trying to load the data of x1. So therefore it turns out that you are reading x2, you are also reading x1 in this case. You are not writing back into any register. So there is no destination register in the store word operation. Therefore, what is the location that we are actually, what is the capture flop that we are talking about? It turns out that this is your data memory. Okay, and that is whichever address we are talking about, you know, x2 minus 10 in this case, right, happens to be that address is the register or the, you know, the memory location which is going to capture this data, and therefore the data has to be ready some setup time before the clock edge there. Okay, that's the key point. Finally, you are trying to do the branch on equal. So you are now taking x1 and x2, you are going to compare them, right, and then you are going to say, okay, if x1 is equal to x2, then make PC equal to PC plus IMM, right, and therefore in this case the PC is the launch flop. You are trying to launch it from the program counter, but eventually you are still trying to only update the program counter back. You are only reading these registers x1 and x2. You are not doing any writing back into the register, and therefore here the capture flop also happens to be the program counter, right. So in order for all these 4 instructions to work, there is a timing constraint where the program counter has to launch something and data has to be ready a setup time before the respective capture flop. Okay, and eventually we need to choose a timing, a clock period such that all these 4 operations can be accommodated in the same clock period, right. So it's not possible to say, okay, I will run only R type of instruction, so I will use the clock period that works for that, then some other instruction may not work. So let us now get into the analysis and see what this whole clock period comes out to be for each of these 4 types of instructions.